Good. Our next speaker is Piotr Miska from Krakow, Poland, who will tell us about Stirling numbers. Please.
Thank you very much for the introduction and for possibility to give a talk to a wide community of mathematicians, number theorists. I would like to talk about my results with Thomas Ward from Newcastle University on non-realizability of Stirling numbers. So let us start with the definition of realizability of a number sequence. Okay, so we say that a sequence is realizable, a sequence of positive integers, if it's the sequence of numbers of fixed points of the consecutive iterations of some set theoretical function t, which acts on some set x. What is important, we don't require any extra properties on the function t. It's only a set theoretical function. Also, the set x can be arbitrary with no extra structures. But what is interesting, in fact, each realizable sequence can be realized as a by some diffeomorphism of class C infinity on an annulus. It is the result of Windsor, and what more, this result is fully constructive. So in fact, if a sequence is realizable, then it is realizable by some smooth invertible mapping. But instead of looking, instead of checking the realizability of a sequence by finding some map, we can only check two arithmetical conditions, namely the dot condition and the sign condition. The dot condition says us that the for each positive integer n should divide the nth term of the convolution of Möbius function and the sequence A. It is the justification is as follows: as an is the number of all points that are periodic with period n, then by Möbius inversion formula we know that the following expression is exactly the number of points contained in the orbits of length exactly equal to n. So this number should be divisible by n. And of course, this number should be also non-negative. So we also need the sign condition. Okay, so the very first example of realizable sequences is the class of powers of some fixed positive integer. And if k is at least equal to 2, then the sequence k to the power of n can be realized by rising to the power of k on the complex plane, simply. Moreover, the set of all the sequences satisfying the dot condition has a structure of an abelian group. It's simply a Z module, and we will also, this is a quite easy remark, and we will use it in the sequel. And also we use another very simple remark, namely the dot condition for n equal to p, a prime number, takes a very simple form, namely p divides the pth ap over a1, the pth term of the sequence minus the first one. So in particular, the sequence of all consecutive positive integers is not realizable, as 2 does not divide to -1. By S1 of nk, we mean the unsigned Stirling numbers of the first kind. It is the numbers of permutations of a set with n elements with exactly k cycles. By S2 of nk, we denote the Stirling numbers of the second kind, which are the numbers of partitions of a set with n elements into k non-empty subsets. As the beginning, if we fix k, then the beginning k minus 1 terms of the sequence are 0, so it does not make sense to consider the sequences S1 and K, where K is fixed and runs through all the positive integers. So we need to shift the variable n, and we consider the sequences of consecutive Stirling numbers with the second argument K, but only those terms that are non-zero ones, namely sk1 is the sequence S1 of n plus k minus 1 k, and sk2 is defined in the analogous way. In particular, S31 and S32 are as follows. And the question is, are the sequences sk1 and sk2, where k is a positive integer, are realizable? And with this question, Tom Ward wrote to me some time ago, because he was able to prove the realizability of sequences sk2 for k at most equal to 2. He also could prove that for k equal to 3 and 4, the sequence sk2 is not realizable. But he wanted to prove this fact to check the realizability for every k. So he asked me for a help, and this is why our work emerged. And in fact, we gave the answer in full generality. At this time, when I was working on Stirling numbers, Tom Ward with Moss showed that the Fibonacci sequence is non-realizable in a very strong way. Namely, for each positive integer r, the multiplicity of the Fibonacci sequence is not realizable. On the other hand, the sequence of Fibonacci numbers with indices being perfect squares also is not realizable, but after multiplication by 5 becomes to be realizable. And this result motivates us to introduce a notion of almost realizability. Namely, we say that a sequence of positive integers is almost realizable if it becomes realizable after multiplication by some positive integer r. And the least such a positive integer r that repairs the realizability of A is called the repair factor of the sequence A. And we denote it by fail of A, because on the other hand, it's of course the measure of failure of the sequence A to be realizable. Let us see that the repair factor of the sequence A is simply the least common multiple of the denominators of the expressions that appear in the Dold condition divisible by n. So we consider also the situation that the least common multiple is infinite. And in fact, we have two two extremal cases. The first extremal case is when a sequence A is realizable, and then the repair factor is equal to 1, and the sequence is not almost realizable, as for example the sequence of Fibonacci numbers, if and only if its repair factor is infinite. So this sequence is not realizable as possibly as it can. Okay, so now we are ready to state our results. The first result is that for each positive integer k, the sequence sk1 is not almost realizable. And the second result shows that the sequences sk2 are realizable for k at most equal to 2, and for k at least equal to 3, they are not realizable, but are almost realizable with repair factor dividing k minus 1 factorial. At first, let us take a look on the proof of realizability of sequences S12 and S22. It is very easy because we can show their realizability by giving appropriate maps. The sequence S12 is the sequence constant equal to 1, so it is realized by an identity map on a singleton. On the other hand, the sequence S22 is exactly the sequence of powers of 2 decreased by 1. So it can be realized as the sequence of numbers of fixed points of iterations of squaring on the unit circle on the complex plane. In the remaining cases, if we want to show that the remaining sequences are not realizable, in fact, we only need to check that the Dold condition fails, as the sign condition is always satisfied. This is because the sequences of Stirling numbers if we want to show that the sequences SK2 are almost realizable, we need to check formally the sign condition, but it is always satisfied as the sequences of Stirling numbers, the Stirling numbers when k is fixed and n grows, they grow quite fast. Namely, by using very simple combinatorial argument, we can obtain the inequality S2 of 2n plus k minus 1. K is at least equal to n times S2 n plus k minus 1 k. And then we can apply the result of Puri, who showed that if the term with index 2n of some increasing sequence of non-negative numbers, real numbers, is at least equal to the n times the nth term, then the sign condition is satisfied. Up to from this moment, we are only focused on the Dold condition, and now let us see why the sequences SK2 are almost realizable. In order to do this, we use the exact formula for the Stirling numbers of the second kind. We multiply by k minus 1 factorial, and then we rewrite the binomial coefficient k over j. And after simple modifications, we see that k minus 1 factorial times S2 of nk is in fact a linear combination of the powers j to the power of n minus 1 with some integral coefficients. And as we know that the sequences of the form j to the power of n are realizable, then also their linear combinations with with integral coefficients satisfy the Dold condition, and we are done. In order to prove the non-realizability of sequences sk1 and sk2, where k is at least equal to 3, we need the following lemma. And in fact, the proof of each of the part of the lemma is, the proofs are very similar. In fact, the proof of the second part is a little bit easier. So we will focus on the first part. And what is the statement of the lemma? The statement of the lemma is that if p is a prime number and k is a positive integer, then S1 of p plus k minus 1k is equivalent to 1 modulo p if and only if k modulo p squared belongs to the set of consecutive integers from p minus 2 times p plus 1 up to p minus 1 times p. And analogously, S2 of p plus k minus 1k is congruent to 1 modulo p if and only if k modulo p squared belongs to the set of consecutive numbers from 1 to p. So in fact, the Dold condition for n equal to p being a prime number holds only for some very special numbers p that satisfy some congruence with number k. So let us take a look on the sketch of the proof of the first part. So let sigma be a set with p plus k minus 1 elements, and we partition this set into k disjoint non-empty cycles. Each of these cycles has length at most equal to p, as each cycle is non-empty. Then we denote by j sub l the number of those indices I that the length of the ith cycle is equal to L. Then, of course, the sum of all j numbers JL is equal to the number of all the cycles, okay? And the sum of L times JL, well, where L runs through all the positive integers from 1 to p, is equal to the size of our set sigma, p plus k minus 1. And then we can obtain the following formula for the number S1 of p plus k minus 1k, where we run through the p tuples J1 to Jp that satisfy the following two equations. And moreover, we see that we can construct in the following number of ways a partition of a set with p plus k minus 1 elements into J1 cycles of length 1, J2 cycles of length 2, J3 cycles of length 3, and so on. Next, we note that for each L at least equal to 2, the number JL is less than P. The number J1 is at most equal to K minus 1, and if JP is positive, then JP is equal to 1, J1 is K minus 1, and every remaining number JL is equal to 0. So if a P tuple J1 up to JP is not of the form K minus 1, 0 up to 0, 1, then JP is equal to 0. And in fact, the summand corresponding to this P tuple in our formula here is divisible by P. So S1 of P plus K minus 1K is congruent to its summand corresponding to this exceptional P tuple K minus 1, 0, 0 up to 0, 1. This summand takes the following form, and in fact, it is congruent to minus ceiling of K over P. And then if we write K in the following way, we see if we write k as n times p squared plus some remainder from division by p squared, then we see that the right hand side, this expression minus ceiling of k over p is equal to 1, if and only if k is of the following form, and we are done. So let us now take to the proof of almost non-realizability, so very strong non-realizability of numbers sk1. So if p is a prime number, and we fix a positive integer k, and then if p is a prime number such that k is at most equal to p minus 2 times p, then the k modulo p square does not belong to the set as in the statement of the lemma. So the Dot condition for n equal to p is not satisfied. But as we see, we have infinitely many such prime numbers p that satisfy this inequality where k is fixed. So in fact, we see that the expressions that appear in the Dot condition divided by p have denominators equal exactly to p. So in fact, we have an infinite set of denominators greater than 1 being pairwise disjoint distinct prime numbers. So the least common multiple of those numbers is infinite. So this, the sequence sk1 is not almost realizable. So for the last part of the talk, the proof of non-realizability of sequences sk2 where k is at least equal to 3. In order to do this, we only need to find for each k only one prime number p such that the Dot condition fails at p. So by our lemma, we only need to find such a p that k belongs, k is greater than p and at most equal to p squared. This condition is equivalent to the following double inequality: p at least equal to the square root of k and at most equal to k. So for k equal to 3, it suffices to take p equal to 2, and for k at least equal to 4, we take we see that the square root of k is at most equal to k half, and then we use the Bertrand postulate to find a prime number p such that the following inequality follows. So the Dot condition fails, and we are done. And that's all I would like to say. So thank you very much for that.
Thank you. Are there any questions for our speaker? Let's check the chat. No. If not, then I thank our speaker again, and we have a break of 5 or 6 minutes. Thank you all.